In this lesson of quadratic graphs and their properties, we're going to be looking at what is meant by the word quadratic, the basic shape of that graph, and some clues that we can draw from its equation. So our target is I will explain how the function y equals ax squared plus c changes for different values of a and for c. So we're going to see when you have the number in front of the x squared, how that affects the graph, and if you have a constant being added to it, how that also affects the graph. So first, by definition, a quadratic function is a function that can be written in the form y equals ax squared plus bx plus c, where a does not equal 0. A can't be 0 because 0 times anything right here would be 0, which would get rid of the x squared term, which would make it no longer a quadratic. Like from what we learned last chapter, quadratic means that the polynomial is to the second degree. Now in this specific lesson, we're looking at equations that do not have this bx term. We are just looking to see how the a and how the c affects that graph. So some examples of these equations would be like y equals 3x squared, or y equals x squared plus 9, or y equals x squared minus x minus 2. Now if that was written as f of x equals 3x squared, that means the same thing. So don't let, when you see those f of x equations, don't let those, make you panic any. It means the same thing as y equals. So if f of x equals x squared or y equals x squared, that is called the parent quadratic function, meaning that that's the basic picture of it. So the graph of a quadratic is a U-shaped curve, and we call that a parabola. It can either point up or it can point down. Now, if we're taking this equation, y equals x squared, if you're going to make a graph, you've been trained that you're going to make a table. So if I put negative 3 into that equation, negative 3 squared is positive 9. If I put negative 2 in there, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0. And then what you'll notice is your numbers start to bounce back. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so forth. So as a graph, it would look something like this. Let me point out to you where these coordinates are. Negative 3, negative 9 is right here. Well, right there. And then negative 2, 4 is right here. Negative 1, 1 is right here. 0, 0. And then this is where we start to bounce back. You have a mirror image on your table in the y values, which creates a reflection across the y-axis. It's a mirror image. It is symmetrical. 1, 1 would be there. 2, 4 would be here. 3, 9 would be here. Now that curve, instead of an exact V, occurs because if you had put 0.5 squared in there, 0.5 would be 0.25 right here. And so if you had the decimal ones in between here and your coordinates were closer together, that would show the curve, and that's what builds that curve there. So our first property of it is if it will open upward or if it opens downward. There's lots of important parts of the graph pointed out in here. So if you see that dashed line, that is that axis of symmetry that I was talking about. You have the vertex of it, or the bounce back point. Like if I were to throw a bouncy ball on the floor, it hits the floor and it bounces back up. Or if I'm shooting a basketball, it hits the arch and this is the point that it starts to come back down. If it is open upward, the vertex is called a minimum because that's the lowest point. If it opens upward, that vertex is called a maximum because that's the highest point of the graph. So if the a term is positive, if the number in front of the x squared term is positive, then the parabola opens up, which makes sense. Positive is up. So some examples of that are y equals 3x squared or y equals 1/3 x squared minus 4. If a is negative, the number in front of the x value, the x squared value, then it's going to open down. So examples would be y equals negative x squared or y equals negative 1/2 x squared plus 3. So let's get some practice of graphing this. We're just going to put about 4 values in here. So I'm going to start with, let's put negative 3 in here. So if I put negative 3 in here, negative 3 squared would be 9, and then 9 times negative 3 would be negative 27. Then let's put negative 1 in there. So negative 3 times negative 1 squared. Negative 1 squared is 1. 1 times negative 3 is negative 3. Okay, if I put, and actually I probably should put a 2 in there because negative 27 is going to be like way down here. So let's go with, let's put 0 in there. Negative 3 times 0 squared would be 0. And so that would be 0. And let's put a positive 2 in here, and then we can make our mirror image on the other side. So if I put 2 in there, 2 squared is 4. 4 times negative 3 is negative 12. So 0, 0, that's pretty easy right there. Negative 1, negative 3 would be here. And so because I know this is a parabola, then if I had put positive 1 in there, 1 squared is 1. 1 times negative 3 is negative 3. And then the 2 brought me down, actually that should be negative 12. Okay. 2, and then that would be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So like way down there. It's off the charts. I know it makes a U-shaped, so it's a very skinny parabola, and it has arrows on that end because it extends infinitely in that direction. Something you should notice is there are no positive y values. So if I were describing the domain and the range of this function, the domain is all real numbers because it's extending infinitely out, but the range is numbers that are, less than or equal to 0. It would never fall up here in quadrant 1 and quadrant 2. So notice how this parabola was really skinny as compared to the parent function, which was not quite as skinny. So when you are comparing widths of parabolas, you're going to use the rule of the 3 little pigs. And this is how the a value changes the parabola. So we've seen how a can make it point up or point down if it's positive or negative, but you also need to see about how it is stretched out. Is it a really skinny graph, or is it a fat, wide graph? So we have the parent function. Here is this piggy, and he says, I'm the parent. I'm kind of a normal height. Well, some people are twice as tall as their parents, and so if you had a 2 there, that pig is going to be stretched up taller. I'm twice as tall as my parent. And then you have the people that are half the size of their parents, like my children, and so they would have a 1/2 in front of their x squared term. I'm half as tall as my parents. You can see how that piggy is shorter. So here is an actual picture of 3 different parabolas being graphed. And so if it's in that term y equals ax squared, this kind of greenish color one here, that is the graph of 2x squared. The graph is skinnier, or in other words, the slope is going to be much steeper. Here we have x squared. And this seems wider because the graph itself is much more zoomed in. Where before you would have had like 1, 2, 3, 4, and positive 1 isn't until right there. The scale is not the same on the x and y axis. This bottom one is 0.5 x squared. And that graph is fatter. In other words, the slope is not quite as steep. So let's see how the c value affects it. In red, you have f of x or y equals x squared plus 3. And in blue, we have the parent function y equals x squared. As you can see, this red one, it's about the same width. It's just shifted up. So here's kind of a conclusion that we can make here. Let's put this back down here. In blue, you have the function table for y equals x squared, and this is like what we saw before. Negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, 0, 0, and here's where it starts to bounce back up, where it's reflecting across its axis of symmetry. The domain, the x value, is all real numbers. The range is just everything that's greater than 0. In red, we have a c term of plus 3. So negative 3 squared is 9, plus 3 is 12. Negative 2 squared is 4, plus 3 is 7. Negative 1 squared is 1, plus 3 is 4. 0 squared is 0, plus 3 is 3. then it bounces back up. So it's the same values as over here, but we're adding 3 each time. So here, the domain is still all real numbers. The x values is going to be any real number. However, the range is starting at positive 3. It's everything greater than or equal to 3. So we can sum that up is that the c value shifts the parabola up and down. Here, it was shifted up because it was adding 3. If that had been x squared minus 3, it would have been written down here. Isn't that a beautiful parabola? So let's look at this equation. Y equals negative x squared plus 3. What clues can we gather from this? So first, it's a negative. So that means it's going to be pointing down. It is a 2, so it's going to be a skinnier graph. It's going to be stretched vertically. And then we have a plus 3, so that means it's going to be shifted up 3 units. So let's get a coordinate plane over here. Let's get that a little smaller. Okay. So if I were to graph this, I know that it's going to start at, or I'm sorry, the vertex is at 0, 0. Whoops. Okay. It is pointing down. Actually, the vertex is not at 0, 0. I lied about that. My apologies. The vertex is shifted up 3. So 1, 2, 3. It's going down and it's really skinny. So it's going to look something like that. So it's down because it's a negative. It's skinny because it has a coefficient of 2, the x squared term does, and it's shifted up 3 units because of the c term plus 3.